Okay guys, we're looking at the Benzyne reaction. Let's move through it. So we're doing the mechanism. We'll redo that real quick here. If we put a lot of pressure and heat on this, we can get a reaction. The hydroxide will actually act as a base. Instead of doing the NAS and attacking that carbon here, it acts as a base. That means it's more preferred here. These electrons take the H, leave those behind, and we can get a anion. Now, some folks will show formations of Benzyne a little bit differently. I'm showing it by making the anion and then moving these in and kicking off the leaving group. And that gives the so-called Benzyne triple bond. Some books very few will just show like an E2 and never show an anion. Take the H, move these in, kick that off. That looks like an E2. What's the hybridization of that carbon there? SP, if you look at it. Well, SP is what type of geometry? Linear. Can these bonds be linear here? No, so it ain't SP. Okay? This is a crazy triple bond. It's really a very weak triple bond. It's really almost not a triple bond. When it's drawn like that, it's called a Benzyne. Because of the bond angles of this ring, it cannot be linear. That means it cannot be SP. It actually remains SP2, and you actually have the two hybrids are interacting side by side. You ever seen hybrids interact side by side? The answer is no. Anytime we've ever seen hybrids, they're head-to-head overlap. This is showing an SP2 carbon, boom, 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 trigonal planar, p orbital left over. P orbital is in the benzene. There's the benzene pi system there. You have the two sigma orbitals that are out here, and they're actually overlapping side to side. Well, how much side to side overlapping are they doing? Not much. Yeah, not much. They're also not like this, but they're like that a little bit. Okay? But still, it's kind of shown like this. Now, there's something else we could show. If you don't show this arrow here, at this point, this can just leave. All right, so I'm going to back up and just show that one arrow. If that just leaves, what do we get? Boom, boom, boom. Minus, what is down here? Plus. Yes. This is another Lewis structure we can show. What are these actually? These are actually resonance structures. Where if you want to show the triple bond, you just take these and move them in, you get the triple bond. Or if you want to go back here, you take the pi bond, I want to call it pi bond. You take the two electrons, you move them out here. Okay? Why would this chlorine just leave? Well, it ain't going to just leave from the starting material, but it would leave here because we're making a neutral molecule. This leaving as an anion is very similar to, you remember carbines? How do we make carbines from chloroform? CHCl3. We treated this with hydroxide. That removed the H, and we made CCl3. The minus. Then one of the chlorines just left. Now it's leaving the same carbon as the minus charge, but when it just leaves, we get just that, and that's a neutral carbon now. Remember the chloroform, the dichlorocarbene? So basically, you can sort of show something like that. Some books show it like this. In the end, I then showed water. This thing is electrophilic, that is, nucleophiles will add to it. The important thing is this is symmetrical. The entire thing is symmetrical. Symmetrical may not be a good word. Of the two carbons here, they're identical. And you can actually attack either one. For example, I'm going to attack up here. If I attack up here, I would then move these down, and that would give boop, boop. We attacked up there, so the water's now bonded there. We haven't lost anything from the oxygen. What's now here? Minus. Ah, yes, I actually have a double bond remaining because there was a triple there. So we have this anion. You can get the same. Remember I said you can work from any resonance structure? Never let anybody tell you you can't. Well, we could have added the water to this resonance structure. Just add it right there. The minuses you don't have to move anything over. It's already been moved over. It's already there. Okay. Basically, we can get to this point. We could have added down here and got the anion there. At this point, well, this is a carbanion base. That looks like H3O plus. You got a built-in acid. This wants to take the H. You want to do a hydride shift? Not a hydride shift, because if we're taking H and 2 electrons, we're going to have an H, 2 electron. You're going to have 4 electrons between the carbon. You don't need a hydride. You need a what? H plus shift. We need just the H. The 2 electrons need to stay behind on the oxygen. Now, a lot of times this is not internal, but this takes an H from another molecule. It has an H on it. And a lot of times I just show H plus transfer. We'll do that a lot moving forward. It's just an internal acid transfer. And when we do that, we go neutral. This becomes OH, lone pair left behind. This picks up the H. I'm not going to draw it in. But it's there. And so there's phenol. Question?
Is this a back bonding of some sort, or is this?
Back bonding what? Here?
Yes.
No, this is probably intermolecular, where you got another molecule. Okay, this comes close to this, and so this takes the H, leaves it behind. This takes the H of another one, and leaves that behind. And you end up with what you want. You want an H here, and you want the H gone there.
Does the carbons being sp2 and planar make it where it can't back bond?
What do you? I don't understand what you want to back bond. What do you mean back bond? You want this to do what?
Well, normally when we have a positive charge next to a negative charge, it would.
You want it to bond to the O?
I think that's what he was talking about.
Or could you just take the hydrogen from the water and bond it?
That's what I'm saying. I mean, usually, okay, this is going to have a transition state. If that takes the H, that's a 1, 2, that's a 4-membered ring you're trying to do there. Okay? This may not be able to reach that with a 4-membered ring. 5 and 6 is going to be easier. So instead, it's probably intermolecular. It takes the H from another molecule. Anytime we do proton transfer, it's usually intermolecular. I mean, why not? It's like you got everybody sitting here. If I'm sitting here, and here's my basic part, and here's my acidic part, is it easier for me to reach around here and take the H, or is it easier to just take the H from her? Right. Reaching right around here, internally, it might be more difficult. But boom, I'll just take it from her. So it's an intermolecular. This takes the H from its neighbor. This gives the H to its neighbor. And we'll do H plus transfers a lot. Basically, you move the H to where the basic side is, and the acidic side gives up the H.
And we just write H plus transfer, right?
Very often in the mechanism you just write H plus transfer. We'll do that a lot with carbonyl chemistry. Okay, this is not the final product. We're doing the first step still. The first step is KOH. This implies a second step, that we're still on the first step. This is with KOH. When this is formed in the presence of KOH, what's going to happen? Hydroxide will take the H, and we will get the phenoxide. Okay? This is in step one. As we said at the end, the first step produces an acidic product. Phenols are acidic in the presence of hydroxide. When you make this, you cannot tell your hydroxide, okay, hydroxide, I want you to only react with this guy. Once we form the product, I want you to ignore the product. Will the hydroxide listen to you?
No.
No, it will not. So actually, you actually need two equivalents of hydroxide. One to essentially displace the chlorine and get the hydroxide on the ring. The other to deprotonate the OH. If you only use one equivalent, you'll only get a 50% max yield. Because half will do this, and the other half, instead of doing this more, will start going over there. Okay? You got to have two full equivalents. Now I give this kind of stupid analogy here. Okay? It's very nice and elegant. I don't know how this came up. It might have just been me originally just being stupid, or there might have been some student help. I don't know. But if you knit a sweater in the pool, in a pool, okay, if you make something in the pool, like knitting a sweater, the sweater at the end will be wet. Okay? You did have to dry it. Okay?
Following you.
Okay? We're making an acidic product under basic conditions. The product's going to be in the basic form when you're done. If you want to put the proton back on, you're going to have to supply a proton with workup. Okay? You can't make a sweater in the pool and then expect it to be dry when you're done. You got to then dry it. Now that has become sort of, I don't know if it still works, but sometimes stupid things help you remember. Any questions about Benzyne? Benzyne requires pretty harsh conditions. Unless you're using a very strong nucleophile. We'll see a very strong nucleophile where you can actually do Benzyne at cold temperature. Okay, do you believe this Benzyne, triple bond stuff?
Yes.
Yes.
Why do you believe it? Would you like to have some proof?
Yeah.
What type of proof would you like?
Yield all or
Or are you willing to just accept this and... Okay, well people, chemists have tried to prove this mechanism. It's very hard to see molecules doing all this. One bit of proof is that the Benzyne will act as a Diels-Alder. Dienophile. If you get this form and have a diene in the reaction at the same time, such a product can be isolated. And such a product typically comes from 4 plus 2. Boom, boom, boom. Good old classical 4 plus 2 Diels-Alder. this gives them. You should be able to see that. Now we know that if you do the chemistry to produce this, okay, and have this in, you get this product. So how else could you get this product? I mean, this came from something like this. So we generate the benzyne somehow. We'll talk more about how just to generate that. We did it up there, but it was in a complete mechanism. Otherwise, how is this going to react with that to give that product? Can you propose any other mechanism theory? You just don't have any mechanism that you can show. But if you believe that the benzyne is formed, then you say, ah, okay, benzyne could react with this. That supports the fact that we must be getting the benzyne. Now, does it prove it 100%? Well, hardly anything is proven 100%. It only takes one piece of evidence to disprove something. But that's some evidence. So benzyne will react as a dienophile if you can generate it and have a diene included in the reaction.
How do you isolate benzyne?
We'll talk about it, generating it on the next page a little bit. Okay, additional proof. Back in the like 1940s or 50s, Dr. John Roberts at Caltech did an experiment which has become very classical. He was looking for additional proof. He was kind of doing some experiments, you know, doing some work in the lab. He came up with the idea of, hey, we're going to have a leaving group on a carbon of the benzene ring, but we're going to label this carbon as C13. Isotopically label it. That can be done. So we start with this with C13. He then did a reaction. This is a benzyne. What's the nucleophile here?
NH2.
Yes, it's NH2 minus, okay? Now that's also a nucleophile, but anytime you have two nucleophiles, you want to use the stronger one, right? Okay? So that's a stronger nucleophile than this, because that's the anion, this is neutral. This is actually done in liquid ammonia. If you cool liquid ammonia to minus 33 degrees or lower, it'll be a liquid. Oh, did I say cool liquid? If you cool gaseous ammonia to negative 33, it will turn into a liquid. You actually use it as a solvent. And then you make the potassium amide by putting in potassium metal. And you can get this form. So basically, here's a nucleophile. Now this is a very strong nucleophile. Ammonia is a pretty strong nucleophile. This is very strong. And this is known to do a benzyne at even cold temperature. So, now my pi bonds are kind of drawn over here instead of over there. So I'm going to use this H over here. Now if this takes the H, I reckon I'll do it stepwise. I'll do it stepwise, just we keep that star, this becomes anion. Plus what? Plus ammonia. Okay, now this can move in here. I'll show the actual triple bond, kick that off. Get the triple bond, that's starred. Boom, boom. So we can generate our benzyne here. As I told you, it does happen here, even at minus 33 with this strong base nucleophile. By the way, the high on the quiz was a 10. There was several 10s. I'm not sure what the low was. I think it was 1. The additional spec problem is posted on the 3rd floor in the glass case. Okay, here's our benzyne. Then ammonia I mean, you could use this, but we have ammonia. If you only use one equivalent, that one equivalent is now used up. We can use ammonia. It's a good enough nucleophile. Okay, we're going to attack this. Which carbon are we going to attack?
Either.
Actually, either one. If you attack here, these move over. We get the nitrogen with 3 H's bonded. That's a plus charge. What's now going to happen?
H plus transfer.
H plus transfer. Okay? But see, you can also, that's A. You can also attack here and move these over this way, and this is B. And if we do that, what do we get? We get the ammonia bonded over here. That's an anion. The start is now an anion. And then what happens?
H plus transfer.
H plus transfer gives that. I've just flipped it around. Basically, the amine is not on the starred carbon, but it's next door. Not on the starred carbon, but it's next door. So, Roberts showed definitively, because he isolated this, and guess what? You got like 50-50 mix here. He said, hey look, half of my nitrogen's on the starred carbon, the carbon 13, but half is on the adjacent carbon. So then he said, so how did this happen? Well, basically what this proves is, it's not just a direct displacement of the bromine. Because remember, when you're doing this, you're not looking at molecules, you're looking at liquids in a flask.
Does this one not require the acid?
No, because this product's not acidic. Amines aren't acidic. And so the base is not going to take the proton and make it a conjugate, make it an anion. So he showed definitively that it's not just a simple displacement of the leaving group. He showed that, and then he said, well, how in the world do you get the nucleophile on the carbon, not where the leaving group is, but on the next door carbon? So tell me how you get it next door.
Benzine mechanism? Benzine mechanism.
This supports the Benzine mechanism, because if you show a Benzyne, then you can say, well, the nucleophile then can attack either carbon. Two carbons become electrophilic or get attacked. So this gave even more support to, hey, this must be the mechanism. And that kind of became a very classical experiment. That's also an example of sort of an isotopical labeling experiment, where you use isotopes to help you figure things out. In the end, isomers are possible. That's essentially isomers up there. But let's look at some very obvious isomers. What do you want to say? You call it perchlorotoluene. If you take perchlorotoluene, react it with the potassium amide. Why am I calling that an amide?
Negatively charged.
A nitrogen anion is called an amide. IDE ending. What's a negative chlorine called? Chloride. IDE ending. A negative nitrogen is called sometimes you call it a nitride. But an amine anion was originally called an amide. Okay, amide. It's unfortunate that that's also a functional group that has a carbonyl. Okay, so as a young organic student, it's a little bit like, oh, an amide was a carbonyl containing functional group. Yeah, okay. It's called a sodium amide. And the short name for this is sodium amide, or sodamide. People call it sodamide. This is basically your strong anion here. Okay? This is Benzyne chemistry. I don't know, it's Benzyne, or is it NAS chemistry?
activating group.
There's no activating group for NAS. There's no strong electron withdrawing group ortho or pair to the chlorine. It's not NAS. Maybe it's EAS. Why is it not EAS?
Because it's negative. The benzene won't attack negatively charged.
Because there's no electrophile here. These are nucleophiles. Okay, you got to assess what we're only doing 3 mechanisms. This is a Benzine mechanism. It can't be any of the others. Okay. Benzyne. What's going to be the intermediate we're going to form here?
Benzyne.
That's quite a good answer there. Benzyne. I'm not going to show mechanism. We already know how to form it. I'm just going to show the Benzyne. There we go. You can put brackets around something that's not isolated. Okay? I usually don't put brackets around every, some mechanisms you see every intermediate structure has a bracket around it. It just means it's not isolated. It's a structure that we're proposing, it's just formed along the way. Not isolated. Then what happens? Ammonia adds. It can either add here or here. We've already done mechanism. If it adds there, you end up with which product? That one. If it adds over here, you end up with which product? That one. I've again flipped it. Okay, but that's it. Can you understand why you would get both of these? Now, which one is formed more? We might not get into that. One of these may be formed more than others. You'd have to look at the resulting anion. I'm not going to take any time to look at that. It may not be 50-50. For example, this one down here is probably not 50-50. Show the 2 major products for this one. And the one over, woo! I've got 3 products over there.
For the first one, the methyl group being in orthopair direction, is that for one or the other? Or is that
It's an orthopair direction for an EAS reaction.
Oh, okay.
Now, it may influence this reaction some, but you can't just say it's an orthopair direction. You're doing a totally different mechanism. But yes, a methyl is still typically an electron donator by induction. You just have to assess it more broadly. You can't just say orthopair direction. Okay. There's no H here, so we're dealing with this H. We can essentially eliminate this. I'm not going to do the complete mechanism each time. We eliminate that. We can make Benzyne over there. Boop, boop, boop. What's going to be the nucleophile that adds to the benzyne carbons? Water. So what type of product are we making? Add water, proton transfer. What's going to be? Phenol. You can work through the mechanism on your own. That, you can draw it wherever you got good. What's the other going to be? Basically, one's ortho and one's meta. Yeah?
Yeah.
In this case, I would say one of these may be preferred over the other. Which one do you think is preferred?
Meta.
Ortho.
Meta.
Which one do you think is preferred?
Oh, no, it'd be that would be
Meta.
Who thinks meta? Who thinks ortho? Why do you think ortho, Myron? But that's for EAS reaction. We're not doing EAS reaction. actually, electronically, it's probably, well, the answer is meta. Electronically, this probably directs at meta. First off, why is it meta? Somebody give me a...
Because if it attacks that top carbon, it kicks the electrons.
Because if it attacks the bottom carbon, maybe it's coming in for attack. I'm going to attack that bottom carbon. Whoop. I'm going to attack the top carbon. Boom. Nothing blocks it. This group maybe blocks it a little bit. I was like, here we go. Oh, I like that carbon. Uh-oh. Here we go. I like that carbon. Bam. Okay. Of course, it's open right through there, but it's not open. Okay. Sterics. Another reason, when we move this over, what does that give? Anion. Okay? Right here. What type of electronic effect does this group have? Donates. Is that going to stabilize the nearby anion? No. No, it goes deep, okay? So here the electronic effect, you don't want an anion nearby a donator. You'd rather have the anion away from the donator. If I were doing reverse, see EAS, there's a positive form in the ring. And this stabilizes a positive, and it best stabilizes an ortho and para. We're not doing EAS. So there's a couple of reasons why I would say that probably your meta is preferred. In the end, though, you'd probably want to show both. You both are sort of major products. But if you were asked to decide between the two, then I would hope you could give an argument to why this one would be probably preferred. Okay, why is that one over there 3 products? Because there's 2 different benzynes that can be formed. You can form benzyne. Now, first off, you can't just look at where the pi bond is. If there's a pi bond. See, here the pi bond is there. And it looks like, wow, we can just eliminate and make it a triple bond. And it's not there. Let's see. The pi bond is there. You can also eliminate here. I mean, neither one of these is correct, right? Really dealing with fully delocalized electrons. You can eliminate HCl here. Basically, there's 2 different benzynes you can get. Because of this group up here, it makes them not identical. You can get benzyne down there. You can also get benzyne like that. Chlorine's gone. You can get nucleophile added here or here. So that's para to the existing group, and this is meta. Or you can get nucleophile added here or here. That's meta to the existing group, and this is ortho. Oh, meta's the same. Basically, you can get your nucleophile ended up para, meta, or ortho to the existing group. I'm not going to draw all 3 of those out, but you just kind of see what I'm saying here. 2 benzynes. There's thus 3 possible places to attack. Does that make sense?
If we were asked to give a major out of 3, could we say that it was the meta because they both have the opportunity to form that?
Sort of twice the chance. Possibly, it gets a little complicated, but that's a good point. You just got twice the chance of getting meta. Yeah, getting a little convoluted. Okay, recognizing when benzyne is taking place, recognizing that isomers are possible, understanding understanding the Benzine mechanism.
Dr. Stevens, how did you get that para-meta enzyme? Did you like just rearrange the?
Yeah.
You remove the H, make anion, and anion moves in, kicks off chlorine. But you have to have the pi bonds oriented so that one is there to begin with.
Yeah, so you have something moving to start with?
Yeah, but see, those are just resonance structures.
Yeah.
Neither one is correct.
Thanks.
Okay, let's finish this up by looking at some sort of miscellaneous. But in terms of the chemistry, it's very straightforward what we're doing. But what else can you do with benzynes? Question was asked earlier, how do you maybe isolate a benzyne? Let's look at stuff. Here's some chemistry. If you take this and treat it with N-butyl lithium, you can make benzyne. Well, here's an H. What is N-butyl lithium? Boom. It's just a carbanion. These electrons, I'll just do it sort of E2 if you allow me to just do it like that so we can go there directly. Sometimes the book, no, I don't want to.
No, don't do that.
Let's don't do this. Let's just.
Why not?
Well, I may need to show the anion. So let me go ahead and show it. These go here. What do we get? We get the anion, the chlorine's still there. Plus what?
Lithium or butane?
Butane. Now in terms of an acid-base reaction, why is this favored? This is favored. I could have showed you this in organic 1 and you should have been, you know, this is favored. This is sp3. Now the anion is what?
SP2.
sp2. It's got more S character, so it's more stable.
Is it also resonated?
No, it's not resonance stabilized. This does not have any resonance. No lone pairs and an sp2 sticking out. Okay? There's no resonance here of the anion. Only thing it has going for it is got more S character than that. So this is just favored by acid base. Then we can move these in, kick off the chlorine. That does give the benzyne. But what nucleophile is around? Do we have any nucleophile?
No.
Is that a nucleophile? No. If you use a base like N-butyl lithium, you can get this and there will be no nucleophile around. Because that's not like water or ammonia. It's not going to attack this. Then you can do other chemistry with that. For example, you can throw in maybe a diene and do Diels-Alder. But let me show you some other. Maybe you could throw in some other type of nucleophile. We ever seen something like this? What's this?
Grignard?
Yeah, this is essentially what?
F.
It's essentially your carbanion. Would that react with the benzyne?
Yeah.
Yes. Which carbon? Top or bottom?
Either.
Either. I'll do top. You do this. So we get a methyl there, and this becomes anion. This sequential type of chemistry is used a lot because it's very versatile. But what we've done up to this point, is there really anything new? In terms of what the chemistry we're doing. I mean, the actual, yes, it's new, but is the mechanism new? No, nucleophile adding, get this. Okay. Now, is there any proton available? That's not going to take a proton from just an alkyl. So it's not going to do a proton transfer. So it's going to sit there. It's going to exist until you put something else, to put in something else. What if we throw in this? That's not like a proton source.
Yeah.
Boom. SN2. I'll draw that as a methyl. What do we get? That there? Ortho-ethyl-toluene. 2-ethyl-toluene. That's some very powerful and versatile chemistry there. But again, there's really nothing new. Here's something a little new. Here's another way to make benzynes. What does magnesium do to a carbon-bromine bond? Forget the other one. It inserts. You get Grignard. And the Grignard is essentially what? Essentially that with a bromine next door, right? Magnesium 2+, bromine minus when you make the Grignard. Okay? Now how could this give you a benzyne? Boom. You then eliminate off the other one. That's a tricky way to make a benzyne from such. Sort of make a Grignard and then boom, it eliminates off the other halogen. See that? Okay, let's look at some synthesis. By the way, front page, there are some questions. I believe at the bottom is benzyne chemistry. Lithium, Grignard, epoxide. Don't forget epoxide chemistry. We got about 5 minutes. Let's look on the back side. Anybody have a suggestion which one you'd like to work? The third one? Third one on the back side? Here?
Yeah.
All right, let's work that one. Starting from benzene. A quick assessment. How do you get chlorines on the ring? Chlorine AlCO3 by NAS reaction. We know how to chlorinate a ring. How do you nitrate a ring? Nitric acid, sulfuric acid catalyst. Okay. Huh. It's like an alpha. How do you get this on the ring?
Reduce the nitro.
NAS. Okay. You could have an amine and maybe alkylate it. But this is also could come from an amino leaving group. For example, if we go back, some chemistry that we can use is if I had chlorine here, nitro, and maybe a leaving group here, maybe another chlorine. If I had this, could you make that? Not benzyne. By the way, NAS will always occur preferentially over benzyne. NAS is easier, as long as NAS has the requirement. Strong electron withdrawing group, halogen orthopara. We can react this with ethylamine and do an NAS reaction. This will displace the chlorine. We can do NAS. How would you make this? You can make this a variety of ways. If we go back and just take off maybe the nitro group, if you had that, if you nitrated it, would you give this?
Yeah.
No matter where you put the nitro group, it's going to be there. So the answer is yes. If we put the nitro group there, it's this. We can nitrate this with nitric acid, H+ catalyst. How are we going to make that? Well, you go back to, if we had this, could you make this? What type of director is that? Orthopara? It's chlorinated. It'll go para. You may also get some ortho. And then how do you make that? Well, you just start with benzene and chlorinate it. Chlorinate, you actually dichlorinate, then nitrate. You need to understand that if you mononitrate this, there's only one product possible. If you draw all four structures, nitro, 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 all four will have the same name. Be the same compound. We could have gone back and if you'd said, well, what if I take off that chlorine? If I have this, can you chlorinate it and get that? It's ortho-para director, that's a meta-director. This is going to direct, we'll go ortho or para. Para. We have this. Which group do you want to put on first from benzene? The chlorine or the nitro? Yes, and then you nitrate it, and it will go ortho. If you put the nitro on first and then try to chlorinate it, you won't get that. It'll go meta to the nitro.
Yeah, the one on the top of the page on that. How do you make that like in the like secondary alcohol? How do you make that?
What if we go back to that? Or let me just draw it so the bromine's here. Doesn't really matter. If you had that, could you make this? What do you want to react that with to get this? Hydroxide. Or water. You could do an SN1 reaction. How do you make this?
Bromine and light.
That there? Bromine and light, benzylic bromination. How do you want to make this?
Obviously, and constant reduction.
You want to just take alkyl benzene and nitrate it?
Yeah.
But that's not.
If you nitrate this, you're going to get that?
Now you have to start
Maybe the other way around.
nitrate.
No, if you nitrate, you cannot do Friedel-Crafts. Friedel-Crafts doesn't work with the nitro group on the ring. What you need is this. You need that, and you need to nitrate that. So that's a meta director. Oh, this is going to be tough. Then how do you get this? Wolf-Kishner, N2H4. Some of you said N2H2, some of you said N2O2. No, it's N2H4 on the quiz. Hydrazine. If you use Clemmensen reduction, you'll probably reduce the nitro group. You don't want to use zinc HCl. How do you make this? Benzene, Friedel-Crafts acylation. We're sort of out of time, guys. There's several in the workbook for multi-step synthesis. We have 5 more minutes. We can do another one. Please work the ones in the workbook. Okay? Mechanisms in the workbook. Test on Monday, very similar format. nomenclature, multiple choice, predictive product, mechanisms, comprehensive spectroscopy. If you have any questions, I'll be around after class. Have a good weekend. See some of you this afternoon.